name is Paul Jungwirth. I'm a freelance programmer in Portland, Oregon. I've been working on adding support for SQL 2011 temporal features to Postgres for a long time, especially application time. Temporal primary and foreign keys landed in V18. At least they're there so far. And I have future patches for temporal update and delete and SQL 2011 periods. If all that gets in, Postgres will be the first RDBMS to support all of SQL 2011 application time. But no one, to my knowledge, has published a benchmark for temporal databases. So I wrote one using the Benchbase framework last year, and I want to show the procedures it includes and how I used those to compare 3 different implementations for temporal foreign keys. You know, they closed the call to papers before they announced who the keynote speaker would be, and that's not really fair, I think. Many people here are more designed than me to design a benchmark. So if you have any feedback at the end of the talk or later in the hallway, I'd be very happy to hear suggestions for improvements. So why does temporal need its own benchmark anyway? Well, it's because every table has 2 extra columns giving the start and end times for when the row is true. Or in Postgres, we can do it with 1 extra column using a range or a multi-range. This means you need a different schema from any other benchmark. And then the temporal primary keys and foreign keys have to include those columns with some extra syntax, and there's special syntax for your updates and deletes. And maybe you also want temporal semantics for inner join, outer join, semi-join, anti-join, aggregates, union, intersect, and except. So you can't really test a temporal database with any existing benchmark that's out there. So are there any temporal schemas already out there that we could borrow, ideally with a data set attached? Richard Snodgrass, who is like the godfather of temporal data, describes a temporal database that he used at the University of Arizona where he taught. It's the Venerable Employee Database. This is used over and over for examples in his book. As far as I can tell, he never shows the DDL to create the tables, even on the CD-ROM. In chapter 5, he does give enough details to suffice for those examples. Here, I'm showing you the tables and the salient columns. As you can see, we've got some old school column names. SSN is the primary key of the employees table. There were no PII concerns in the 1990s. PCN is the primary key in positions. Initially, incumbents is the only temporal table here. You can see it start and end columns. There's another more fully fleshed out example in chapter 11, but I'll skip that one for now. Then there are benchmark results reported in this temporal paper by Dignos, Bolin, and Gomper in 2012, probably my favorite of all temporal papers. You might remember it. The authors submitted a patch in 2016 to Postgres implementing what's in this paper. And it includes a performance comparison of plain SQL versus the new exec node that they implemented. They say they're using the incumbent data set, a temporal database about employees from the University of Arizona with columns named PCN and SSN. But I've never been able to find this published anywhere. I emailed the authors but didn't receive an answer about it. And they also don't publish their SQL for an outer join whose performance they compare to their patch Postgres node. And also, as you see here, their benchmarks use a default work mem and no indexes. So I would love to run these benchmarks myself, maybe trying a little bit harder to improve the performance of the SQL implementation, but I can't do that. So I wrote my own benchmark using a tool called Benchbase. This is a Java-based framework from Carnegie Mellon published in 2013. Originally, it was called OLTP Bench, at some point renamed to Benchbase. You can find both repos on GitHub still, and this is the paper announcing it. It contains about 20 benchmarks that you can run on about 20 different database vendors. TPCC is in there, TPCH. There's some real-world data sets like Twitter and Wikipedia. There are micro benchmarks like SIBench and YCSB. Each benchmark defines a schema, a way to load it up with initial data, and then a bunch of procedures that make up the benchmark workload. When you execute a benchmark, you can tweak a whole bunch of options, including which procedures to run in what proportion, in what order. So there's really a lot of potential for experimenting with your own workloads. I talked about all of this last summer in Portland, and today I have to cover more material with half the time. So I'm not going to say too much about Benchbase, but if you're interested in trying it out and configuring it, you can find my previous talks slides in the references at the end of this one. So my benchmark has just two tables, employees and positions, of course. And this is enough to test what we want. To benchmark just primary keys, we'll use inserts. We can benchmark temporal updates and deletes. We can benchmark joins and other binary relational operations. And the big one for me right now, benchmarking temporal foreign keys. Some of this you can do against a V18 Postgres database, but for temporal updates and deletes, you'll need to apply my outstanding patches. So here's a simple example of a procedure in Benchbase. It adds a new position assigned to a given employee. So we have a SQL statement, and we have just some standard JDBC to execute it. Here are the procedures I've defined so far. These are all pretty normal. Insert, update, delete, select one, select all. There's procedures for inner join, left outer join, semi-join, and anti-join. This is the most interesting part, I think, and that is an actual contribution to the state of the art, because no one has ever published SQL to do several of these things with temporal data before. And they're based on a GitHub repo I have that documents the patterns that you can use and validates them with a few tests. So as Benchbase chooses these procedures, it feeds them into a worker class that you write, which can do things like pick the inputs to give to your procedures. The framework has some nice helpers, like getting Gaussian or Zipf random numbers so that your data is more realistic. For instance, some employees will hold more positions and thus get more updates, and so their ID will have more records. And it's nice just to not have flat random for everything. So as I said, the main thing I've done so far is to measure my foreign keys patch. Peter Eisentraut asked about a year ago for this on the mailing list, questions like, have you made sure that it uses an index? Well, using an index is easy to check, but I wanted some defensible numbers, and I wanted to start building a temporal benchmark anyway. But numbers would be hard to interpret if you can't compare them to something. So I thought it would be interesting to compare 3 different ways of implementing temporal foreign keys. Snodgrass gives a query in his book. It's about 1 page of SQL. I'll show it in a second. I'll call it the exists implementation. There's also SQL from Vic Fearing's periods extension, which is excellent and gives you a way to do this kind of thing in Postgres right now without waiting for it to get into core. I think the main insight in his implementation is using window functions, especially lag, so I'll call it the lag implementation. And there's the SQL that I used in my patch, which uses Postgres ranges and multi-ranges, especially a function called rangeag. So to compare them, I wanted 3 Postgres clusters, each running under a different implementation. I took my foreign keys patch, I added some ifdefs so that I had a compile time option to use whichever implementation I wanted. I built 3 clusters. I never submitted that version of the patch to the mailing list, of course, but if you're interested, it's in my personal Postgres GitHub repo. And so then I could put together a workload in my benchmark doing updates, deletes, and inserts to fire the foreign key triggers. Here's part 1 of the OG foreign keys implementation. In Snodgrass, this is actually a check constraint, which you can't do it that way in Postgres, so I had to rewrite it. Like any foreign key, it's a constraint trigger, so that inverts the logic. The book Snodgrass is asking, is every record valid? In Postgres, a constraint trigger is asking, is any record invalid? That probably makes things faster, actually. Originally, he has 3 big parts joined by ORs. Now we have 3 big parts joined by ANDs. In my experience, Postgres has trouble with ORs, so that might help. And also, in his version, the entire thing is wrapped up in a not exists, and that layer disappears for us here. Also, you can see I'm adapting the range columns, which we need because of the temporal primary key, to start and end dates to match his way of doing things. And one part of that is interpreting how ranges use null to signify unbounded to some kind of sentinel value, which we can use plus and minus infinity. In one of my not yet committed patches, I have added support for SQL 2011 periods, so that if you want to have separate start and end columns, you can do that also. But there will still be a generated hidden range column behind the scenes for the primary key. So part 1 here, Snodgrass asks if the start of the referencing record is covered. That's what you see here. Here's part 2. He asks if the end of the referencing record is covered. Notice all these less thans and less than or equals that all have to be exactly right. I checked these over and over. One benefit of implementing a compile time option in my patch was that I could run my regress tests on it and make sure that all of these alternative implementations actually gave correct results. Here's part 3.5. We found a record to cover the start. We found a record to cover the end. Now we have to make sure that there's no gaps in the middle. In other words, there's no record that ends early unless there's another record that picks up immediately where it left off. That's just putting into words what's going on here with these nested not exists. Okay, here's the plan for it. As you can see, it's pretty complicated. It's 22 rows. You can see the tripartite structure. Technically, so that's Snodgrass's version. Technically, we need 3 queries here because we need foreign key checks under different conditions, right? When a primary key is deleted or updated, we want to check for foreign keys that are now invalid. When a foreign key is inserted or updated, we need to check for the primary keys that make it valid. And then we need to check everything when you first create the constraint. Today, I'm just going to talk about checking the check that happens when you insert a new foreign key row or update a foreign key row. In practice, all the queries are extremely similar anyway. Here's SQL for VIX implementation. As you can see, this is a lot simpler. It fits on one slide. This is not exactly what he has, again, but I tried to be faithful to the original. Again, I had to adapt ranges to separate start and end columns and use a sentinel value instead of null. I did use a range operator here, as well as in the exists implementation, so that all 3 implementations could go straight to the relevant rows using the gist index, because it didn't seem like a fair comparison otherwise. Conceptually, this is a lot like Snodgrass's idea. It checks that the beginning of the reference is covered, it checks that the end is covered, and it checks that there are no gaps. But instead of those nested not exists, we can use window functions. Here's the plan for this SQL. It's only 12 lines, so saving nearly half of the exec nodes. We're using an index. As you can see, we're doing a sort to feed into our window function, and then there is another aggregate at the top to look for gaps. Here's the rangeag implementation. I like that it's the simplest. Hopefully that means that it will do the least work. We find all the relevant records in the reference table, then we combine them and make sure that they include the referencing range. You could almost write this without a subquery at all, but for key share doesn't support aggregate queries, and so that's why the subquery is required here. That's something that I would love to improve someday, actually. Performance aside, note that this is the only implementation that supports multi-ranges and potentially any user-defined type for which you can supply an aggregate function and operators for overlaps and contained by. I think you need intersect also. So this leaves the door open to support spatial types, box, or whatever a user can imagine. And I like that that brings forward Postgres' heritage of extensibility. Also, it lets you have ranges over any type, not just date and timestamp, which are the only types required by the standard. And those other types might not have nice sentinel values like plus minus infinity. So having the convention in ranges to use nulls for unbounded is a nice thing too. Here's the plan for it. It's only 6 rows. We're using the index. There's no sort and just one aggregation. Truthfully, the sort is happening. It's just happening inside of rangeag. But still, I think we're saving some time compared to all the separate function calls to lag, array ag, null if, min, and max. It does seem like Postgres can have a high overhead for function calls. So this I expect to help a bit. So my hypothesis is that rangeag will be fastest, lag also very good, and exists really slow. So it's time to run some benchmarks. There are 4 ways to trigger a foreign key check, so let's fire them all. The first thing I noticed is that there is not a whole lot of difference between the implementations. In all the noise of doing an insert or an update or whatever, it was hard to find a signal. Also, it was kind of annoying running 3 separate clusters and doing a benchmark against one, and then a benchmark against another, and a benchmark against another. So I switched my approach, and I added more Benchbase procedures that just run the foreign key SQL directly. So now I'm moving away from a real-life workflow to a targeted micro benchmark, but it should help us to highlight the perf differences between the implementations. Actually, it was still a little hard to distinguish differences, although I could see differences running the SQL casually in pSQL. So it turns out Benchbase does a commit after every transaction, and even though there was no writes happening, this was still causing a delay that was at least 10 times as long as the query itself. So I went a little crazy. I switched to no fsync and tried the benchmark again. Another nice thing is that now I could run all 3 procedures simultaneously as one benchmark without a patched Postgres. I just gave each procedure 33% of the workload, and 1% I gave to my no-op procedure that you might have noticed before. This also means that any non-benchmark activity on the box should affect all implementations equally, since they're all running at the same time. So at the 95th percentile, my guess is basically confirmed. Here's latency. You can see the blue rangeag line is consistently at the bottom, and the green exists line is almost always at the top. Wait, but in mean latency, exists is way faster. So what is going on here? I thought maybe it was erroring out or something. Upon closer look at the Benchbase results, I saw that over half the transactions were failing because of an invalid foreign key. So maybe that was a clue. Here is an explain analyze from one of the exists transactions. Most of the plan never executed. So this is a 3-part and the first part was false, so the rest short-circuited because Postgres is really smart. Just to confirm, I even wrote a little bpftrace script to count the calls happening to exec proc node, and it showed that queries checking invalid references made half the calls compared to checking valid ones. But this is totally unrealistic in any app that I've worked on, right? You don't have 60% foreign key failures in your applications. At least how I use them is as a guardrail to preserve integrity. And if I've got something's ID, I expect it to be there 99% of the time, especially with surrogate keys. So I tuned my load script to have 1% failures instead, and I tried it again. Here's 95% latency. Rangeag has the lowest latency here. You can see what I mean about noise affecting everybody the same. Here's median latency, and here's mean latency. So in this case, exists is back to being this lowest again. It only outperforms when most of the checks are for invalid records. And in full disclosure, this story actually happened last summer, and I had trouble reproducing even this much more recently. I like this story because it was a surprise and it took some work to make sense of. But when I was generating newer graphs a few weeks ago, I couldn't make exists faster no matter how many errors I caused. So perhaps there was an additional condition required to cause that imbalance. I'd like to do some more digging here, but I ran out of time. Here's throughput, by the way. I can't see anything in there. I thought that I would see a difference. Maybe this is because I told Benchbase to give everything 33% of the workload, and so everything is doing the same number of jobs. I'm not sure yet, but I'd like to do some more digging here as well. So then I wanted to try some simple variations. But previously I was running with 100,000 employees. Here's a benchmark with 10 million employees. We get the same results as before. Here's median latency and mean latency, nothing surprising here. So what if there's a long salary history, right? What if every year we give an employee a raise so that employee 5 has a whole bunch of records, right? Like one for every row as their salary goes up. This means that foreign key checks should be a little bit harder, right? Because now the position record, which hasn't changed, needs all of those employee records combined to fulfill its valid time. So I thought rangeag might be worse here because it has to combine all those rows into a multi-range. So I added this code as an optional part of the load step, which is run before the benchmark executes to prepare the data and give people a history of raises. And these are the results I got. Here's 95% latency. Again, range ag is faster. So I guess the extra records are affecting everyone equally, or at least are not a significant factor. Here's median latency, the same result as before, and nothing surprising in mean latency. So that's what I've done so far. There's a lot more I would like to do. So far, all my serious experiments have been with foreign key implementations. Even there's more I would like to do. I mentioned having numbers are not helpful without a comparison. So what I would really like to do is design a workload, run it with and without foreign keys, and find out what they're costing you. And then maybe do a similar workload with non-temporal tables and see what non-temporal foreign keys cost you. And then I would have some idea of like how much extra is it to have temporal foreign keys. That's all a lot of work, but I hope to do it soon. And then there's lots beyond foreign keys. I have several competing SQL implementations for outer join and other things, and so I want to compare those, which I can do with this framework. And if I can get that old Dignos patch to apply after all these years, I would love to try reverse engineering his results after SQL 2011 is all implemented. And then I would like to collect more stats like CPU and I/O, and also would like to revise the benchmark to use SQL 2011 periods instead of range types so that it's not Postgres specific. And then you can start comparing different RDBMS vendors as well for their temporal features, although there's not much out there besides Postgres to compare at this point. Here is a list of references. And here's a link to just this talk, which has the slides and everything else, and will get you to all those other links that I showed a second ago. So thank you for your attention, and I'm happy for questions or any feedback.